gonna just continue to cover the basics of convex optimization. So last time, Ina talked about convex function and convex set, and today I'm gonna just briefly discuss the different types of convex optimization. They are linear programming, LP, QP, quadratic programming, quadratic constrained quadratic programming, second order cone programming, SOCP, and lastly the big boss, SDP, semi-definite programming. And these optimization programs are a specific class of the general convex optimization program. And everything on the right contains the optimization programs on the left. So basically, I mean, LP can be formulated as a special case of QP and everything else. So it's monotonic. Bear in mind that in this definition, we assume QP and QCQP are convex version of QP and QCQP. So we'll see what that means in a while. By the way, if you think this is too basic and too simple, just let me know so that I can go directly to the examples. And if I have time, I'll be able to cover the duality theory and give some ideas how to use Finchel conjugate to compute the dual optimization program, which comes pretty handy when we solve actual problems. So on this list, from left to right, on the left, LP is the fastest to solve, and SDP has the worst time complexity. But SDP is the most general of all these optimization programs, so that we can use it to build more versatile model. That said, even just the simple linear programming itself is very useful and is widely used in both academia and in the industry, especially in the business world. I would say that on this end, this is a line that divides art and technology. Since LP, QP, and QCQP, and etc. have really fast solvers. For example, Cplex. Cplex is now freely available for the academic use. It's provided by IBM, and it's really fast. It's able to solve problems like at the scale of 10 to the power of 5 to 7 variables and constraints. On the other hand, for the semi-definite programs, what we have is things like CDUMI and SDPT3, and we can use CVX to do that. But it only applies to really small scale problems, so we can't really test like an algorithm with CVS on any realistic scale, realistic data set on the internet. So, okay, so now let me start to give some standard forms of all these optimization programs and give some examples for each. So, starting from LP. So, I'm writing the general form of LP, although it is different from the so-called standard form or canonical form. But any LP can be reformulated as this. So these are, because all the objective and constraints are affine functions, that's why we call it linear programming. And we can just imagine this, we minimize the cost of an operation, and X is something we want to, we have decision we need to make decision about like how many items to purchase, and C, the vector C gives the cost of each item, and the constraints gives the demand of the market, for example. Yeah, so it's either minimizing cost or maximizing profit by using by mathematically formulate them into equations and then solve it with the software. Any of you can give an example of an LP. So just any example. Okay, I'll give one. For example, we have a diet problem. We want to satisfy some nutritional need, and we want to make sure that we use the least amount of money to satisfy our diet requirement. So the diet requirement is given by the constraint, and the cost is given by the objective, and X is the quantity of each type of food we purchase and eat every week. So another example will be just max flow, min cut. So suppose we have a graph which has a source and different nodes in between, and we have a sink or terminal. So we have a source, we have a terminal, and suppose it's a pipe, a graph of pipelines, and we want to push the maximum amount of liquid from source over the pipe of graphs to the terminal T. So how are we going to do that? And we know each section of the pipe have certain capacity constraints on it. So that can be formulated as a weight of this graph. Say this is node 1, 2, 3, 4, 5, and each of the edge S1 has the weight CS1. So that is to say that if we want to formulate it into a linear program, we will maximize F, that is a flow, over a vector of liquid we push through each one of these pipe. So subject to several different things. First of all, the Fij should be smaller than Cij, so that the capacity constraint is satisfied. And then we know for all the internal nodes, for any nodes that is not S and T, the net inflow and outflow actually gives you 0, so it's basically Kirchhoff law. So I don't want to write it nicely here. You can always have my scanned node afterwards. And a next constraint is for the source S. The inflow minus the outflow equals to F. And for the terminal, the outflow minus the inflow equals to F. And all these constraints are linear. And lastly, we want this Fij to be greater than 0. I'm ignoring some constraints in here. It turns out that the dual of this problem is the so-called min cut problem. And the min cut is to choose a cut of the edges that separate the source and the terminal, so that the weight it cuts off is minimum. That's a so-called min cut problem. The sum of weight is minimum. And that is essentially the dual of this problem. So they are giving the same F, no matter whether we solve the max flow or min cut. So that's only LP application I'm gonna give, but just bear in mind that linear programming is often more useful than you think. I'm going to give another example that transforms a really non-trivial optimization, actually a non-convex optimization, into an LP so that we can solve it. this is the so-called linear fractional programs. It takes the form of the ratio of two affine functions. Subject to some linear constraints. Anyone can see that this is not a convex function. Oh yeah, I need the denominator to be greater than 0 too. So anyone can see that in this domain that this function is not a convex function. So just give an example. Suppose we take x to be one-dimensional and take c and e to be just one, and then we take then we can take the f to be 2 and d to be 1. So this is x plus 1 and x plus 2, right? Then I can transform it into x plus 2 minus 1, x plus 2 equals to 1 minus 1, right? And this function looks like this. So it is a concave function instead of a convex function. Okay, let me just remove this. So how are we going to solve this? So one way to transform this to a linear program is to introduce a change of variable by defining y equals to x divided by e transpose x plus f, and z equals to 1 divided by e transpose x plus f. In this way, the minimization becomes minimize c transpose y plus dz subject to g y smaller than hz, and yeah, these are just a constraint here, and we make this to be 1. Furthermore, they must be greater than 0. So by doing the trivial type of change of variable, we are able to transform a non-convex optimization into a linear program, which can be solved really efficiently. So let me just briefly mention the motivation of doing this. So why do we care about the ratio of linear functions instead of just the difference of it? For example, suppose this is the profit, and this is the cost. Sometimes we are more interested to maximize the return on investment or return on asset, which is a ratio, instead of taking the difference. Say if I invest $1,000, I can earn $100. But if there's another option that I can just invest like $1 and I can earn $99, then using the ratio will pick the other option, which is obviously more appropriate out, instead of finding the optimal solution that earns only $1 extra with over 900 more investment. So that's why we care about these kind of programs. So enough for LP. I also just want to point out that because LP is so fast, sometimes we can embed it in the algorithm that we designed and use it to solve a subroutine of the algorithm. One really cool example of this is a 2011 best paper at CVPR. They used an LP sensitivity analysis to find the Newton-like algorithm to solve the L1 version of matrix factorization. So, in other words, robust matrix factorization. And it got the best paper award at the conference. So, now for LP, QP. QP is just a tiny generalization of LP. Instead of minimize linear function, it minimizes a quadratic function instead. So, again, subject to some linear constraint. So that's the usual form of QP. And we need this P to be positive semi-definite in order for this QP to be convex. You definitely know many of the problems that we are interested in machine learning and in statistics are actually a QP. For example, the ordinary least square. If we have overdetermined system of linear equations and we want it to fit it to B, so how are we going to solve it and minimize error? Because it cannot be exactly solved. One way of doing this is to minimize the norm of ax minus b square is to do that, and that is a QP. If we just expand the square. Another example is soft thresholding operator. That is you know soft thresholding operator, right? It's the most one of the most important proximal operator, defined as an optimization that looks like this. Minimize. So it's basically minimizing the quadratic term plus a one norm of x, minimize over x. And this is a so-called soft thresholding operator. It's used frequently in lasso and almost anything that use proximal gradient descent algorithm to solve optimization framework related to L1 norm. So this is almost always used. And it's a QP. In fact, although it's a QP, we can solve it more efficiently than QP. I'm just putting this here so that you know it is a quadratic programming. This can actually be solved in by doing a simple entry-wise thresholding. So it's ON algorithm. Max norms?
Mixed norms?
No, this is not mixed norms. It's just a one norm. Yeah. Mixed norm will come. It's mixed norm minimization or group sparsity minimization is a type of SOCP, second order cone programming. I'll get to that in a while. And maybe you should know this, but lasso and ridge regression and SVM they are all QP. Mainly for the first two, it's because it assumes this form, but only with another regularization term at the back. For the ridge regression, the regularization is quadratic, so it's QP. And both these two terms are quadratic. We can combine them together into a single quadratic P, and then they can be transformed into the standard form of QP. And for lasso, is basically this plus a L1 norm. And L1 norm is only a linear objective, so it doesn't change anything. So for SVM, if you still remember in 701 that we are minimizing something like this, subject to some constraint, and this is essentially to maximize the margin of separation, and that's considered. That can be reformulated as a QP as well, and soft margin SVM too. So it's like just QP. It is already covering most of the interesting stuffs we talked about in 701.
The SVM is a linear kernel, right? With the general kernel.
Yeah, with kernel it's different. But if you look at in the kernel space where it's just a larger dimensional vector, then it still reduces to QP. Yeah. So can I come to this side? Okay. QCQP. So the quadratically constrained quadratic programming, as the name suggests, is simply to change the constraints to allow for quadratic constraints. So it is still to minimize x over xp0 plus, oh, it's up there. Subject to and linear constraints also allowed. So this is a QCQP. So as we can see, the difference is only that we put a quadratic constraint instead of needing everything to be linear. And geometrically, this intersection of these quadratic constraints is actually an intersection of ellipsoid. So if Pi is a strictly positive definite matrix, this defines an ellipsoid. So visually, the constraint set of a QCQP look like this. And if we count the last thing, it cuts this over. So this line is a feasible set of a QCQP. And we are minimizing another quadratic function, so intuitively this should work. Examples of this QCQP, there are also many different examples. For example, in the original version of the lasso, instead of the unconstrained form, lasso is defined to be this. Minimize ax minus b subject to the one norm of x to be smaller than some parameter, say eta. Oh no, this is actually a linear. Well, this is actually a QP instead of a QCQP. But let's just change this to elastic net. So elastic net has this thing. Plus lambda, this is a parameter, x, the two norms square is smaller than some parameter, eta. So this elastic net in its constraint form is a QCQP because up here in the objective, it is quadratic objective, and we have also a quadratic constraint. So there's nothing fancy about this QCQP and QP. So as long as you can formulate the problem into this form, there are existing tools that you can download that help you solve them in almost no time, as long as your problem is not very ill-posed. So, got a question there? Oh, okay.
I'm not quite sure what's the constraints mean.
Oh, this? Oh, elastic net. So the idea is that if you only have a one norm constraint, sometimes it's not unique. And if there are two identical vectors and you are penalizing the one norm, and it will, the stability is really bad because you can arbitrarily choose any one of them or any convex combination of them, and the objective value will be the same. Here, if we put a quadratic term here, it serves as a regularization, and it is elastic net is simply something that bridges ridge and lasso. So when you tune lambda here, when lambda goes to infinity, it becomes a ridge regression, and when lambda goes to 0, it becomes a lasso. So yeah, it usually comes in the objective, so that it's an unconstrained optimization. Yeah.
May I ask you what kind of tools you can use for solving QCQP?
For QCQP, I'm not sure, but Excel should definitely have a built-in module since it's nowadays quite used quite often in the industry too. But as I will show later, this QCQP is it's just a special case of second-order Cohn programming, and second-order Cohn programming is more, well, I'd say more useful than simply this. And you can use a second-order Cohn programming toolbox to solve QCQP too. From all I know, Cplex is likely the best solver for LP and mixed integer programming. And for SDP, since all the generic tools are pretty slow, so I guess CVX together with their academic alliance that give you the access to toolbox like Jirobi will be able to help you out in SDP and many of the other types of optimization. But definitely use Cplex when you try to solve LP really fast. Oh, speaking of computational complexity, most of these algorithms, most of these optimization programs have polynomial time solvable algorithm, but they usually exclude some special cases. And although it's polynomial time, the exponent is usually quite bad. So we don't typically use that for LP. And but instead we use simplex algorithm. And simplex algorithm armed with many specially designed heuristic can work really well in practice. Although theoretically there are cases where simplex method needs exponential time to solve an LP. So this is a second-order Cohn programming. And let me just first write out its form and then illustrate what second-order Cohn means. Actually, Alex has talked in class and he drew a very intuitive plot on the constraints. And I'm just going to replicate that. So we have a norm here. Yeah. So this is the key of second-order Hom programming. It is a two-norm of a Fn function, and we assign it to be smaller than another Fn function. Let's visualize it like this by consider just a special case. Suppose this b and d are all 0, and this ai selects the first two elements of x, and let x equals to x1, x2, and x3, so that we can visualize it in 3 dimensions. This AI selects the first two elements of x, and this CI being 0, 1 selects the last. So this constraint will look like this: x1, x2, x3. Yeah, this is just a coordinate, can you all see this is a cone? This is a cone pointing upwards, pointing downwards, but with an opening going up. So this is x3, and we are saying that the norm of x1 square plus x2 square, and we take the square root, it is smaller than x3. So that gives us a cone. That gives us a cone surrounding the x3 axis. So, like you mentioned just now, one of the example of SOCP is simply the group sparsity kind of penalty. So that's what I'm going to show you now.
So the LHS and the constraint is not a norm. It's CIX plus DI. You always choose a single in this SOCP formulation.
Say it again.
CIX plus DI.
CIX plus DI is something on the right-hand side.
Sorry, what?
This is not a norm. This is just a Fn function.
Which chooses one of the x's necessarily. It will be like 0, 0, 1. That's what you said, right?
Yeah, oh, okay, sorry. These are all xi. Yeah, sorry. So, well, no. Yeah, x is a vector, and ci is a vector too. So it can be any linear function. Yeah. But
so the LHS itself is a scalar, right? AIX plus B, DI.
Which one is a scalar?
AIX plus BI will be a scalar, right?
Yeah. Yeah, this is not a scalar, but if we take a norm, it becomes a scalar. The norm is this form, x2 norm. So the left-hand side and right-hand side are both scalar.
Yeah.
Okay. So example 1 here. Group sparsity. So we are minimizing sum of I equals to 1 to k. Let's just say it's 2 norm. And suppose this is a vector x, and I break it up into k chunks. And the group sparsity is simply to minimize the sum of the 2 norm of each chunk, so that we hope that we can promote the sparsity in the number of chunks instead of number of entries in X. And it can be subject to any linear constraints and smaller than equal to constraint. I'll just write it X belongs to a polytope. Well, to see how this can be reduced to a second order Cone program, we need to introduce dummy variable again. So let yi to be greater than xi to norm. Then doing this is essentially the same as, I need to write over here because I'm running out of space. This is essentially the same as we minimize sum of I equals to 1 to k yi subject to yi is greater than, and also x belonging to the polytope that we had before. So as you can see, this is a second order Cone constraint, and this is a linear objective, so it fits in exactly the shape here, right? Perhaps the most important application of second order Cone programming is the robust optimization and stochastic optimization. So we call this example 2. Robust optimization and so I'm just going to consider the robust linear programming and stochastic linear programming at the moment, and let me write out the forms. These are a very well developed field, starting from say 80s, by authors like Nemirovsky and Bento and etc. So they deal with uncertainties in the model. It's going to be clear as soon as I write this out. Sorry. Do I get an eraser? So this is a so-called robust optimization, and it is a linear program with infinite number of constraints, because this is a so-called uncertainty set. We need the constraint to be satisfied for any AI belonging to this uncertainty set. So a linear program with infinite number of constraints turns out to be a QCQP. And let me just write out the stochastic optimization. It is very similar. It also minimizes the same objective function, but instead of this type of constraint, it is subject to a probabilistic constraint or a chance constraint. So it's the probability of AI transpose X smaller than BI must be greater than 1 minus some small probability. So again, this is also a somewhat non-trivial optimization to solve. Oh yeah, here AI belongs to some probability distribution. Yeah, both these two are designed to handle the uncertainty in the model. Say say we are trying to maximize the profit of my company, but we are not sure whether our data is correct, whether it is corrupted by noise or not. We don't want our solution to converge to somewhere which is really fragile. Whenever this AI changes a little bit, then our profit drop a lot. So that's the motivation of developing such robust optimization so that it can handle everything within the uncertainty set. Or if we model AI stochastically, it can be it can work really well with large probability. So.
Is there any restriction on the uncertainty set? It has to be convex or something?
Well, here as an example, we are just going to be assuming this uncertainty set to be an ellipsoid, or rather a ball.
Then it would be conic, but if it's not the ellipsoid, would it be a conic?
Yeah, if it is not ellipsoid, then it wouldn't be an SOCP. Yeah, that's a very good point. So, so let's say this uncertainty set equals to AI. We consider this as something like a mean, and PI. This is the same as PI up there times U, and for any U that has norm smaller than 1. Yeah, if this is uncertainty set, then we know the sup of all U this is equal to so you see, if we impose a constraint over the sup, which is the same as that, to be smaller than bi, then this becomes a second-order cone constraint. Similarly, for the stochastic optimization, we might assume this AI to be a normal distribution, just for simplicity. Okay, and with that, we know the normal distribution, that probability of, yeah, and because we consider x to be fixed, so the probability of alpha I transpose x smaller than bi is just a scale and shift of the normal distribution, so that this random variable this random variable, meaning that this AI transpose x is also following a normal distribution. So I'm trying to convince you that this thing is actually the CDF function of normal distribution divided by something like and because it is a normal CDF, we know what is an inverse CDF function, so that we can inverse that, and eventually we'll get a constraint that looks like one minus delta, because of one minus delta probability constraint here. So again, this is a constant, and this is a linear term, and this is also a linear term, and it becomes a second order Coulomb constraint. So let me just draw this visually. Suppose this is a polytope of all the feasible solutions. What robust optimization and stochastic optimization do is to make sure that the solution they pick holds for all the C that is within a ball, and because of the equations, because of the equations that transform the uncertainty from alpha to x, to a scaled version of x, this is equivalent to say that we want the constraint to be satisfied for every single point within this ball. That's why we only need to consider the soup, that is this point. So it is like to say that we somehow shrink of a feasible region a little bit so that we have a larger margin of not going outside the feasible region due to the underlying randomness of the model. So I hope this picture is explain the math a little bit.
May I ask you how the soup that line?
This?
Yeah, it's not very clear.
Oh yeah. First of all, we can first multiply this x into that, so we get the first term, right? And for the second term, for the second term, it is actually the operator. It is actually the operator norm of this. It is actually the largest possible value of that, because I'm taking an inner product of this vector with x, so it is upper bounded by. So it is upper bounded by. Wow, this is an x. Really sorry. This is an x. And this u is it's something that is smaller than 1. So this is an x. So that's what we get here. Yeah. Thanks for pointing that out. I had a typo. We only have 8 minutes to cover the semi-definite programs. So. Luckily, Alex has already covered the most important example of semi-definite programs in class. That is the max cut problem. So I'm just writing out the general form of a semi-definite program and give you one example on how it is used to solve the nuclear norm minimization and eigenvalue minimization problem. So these are just vectors, and all the semi-definite programs can be written in this form with a linear constraint and a linear matrix inequality. 1 plus x2 f2 plus 2x in f in plus g to be positive definite. And in the standard form, they also have ax equals to b here. So all these fi, they are symmetric matrices. All the fi and g is also symmetric matrices. And x1, x2, they are all just entries of the vector x, so they are scalars. In fact, we can actually remove this linear constraint and add it into to LMI by making this diagonal AI times xi sum equals to b. They are all diagonal matrices. So we can concatenate this with that, and the equality constraint is simply this and also that. So we can combine the Fn constraint with the LMI so that eventually we can express all the SDP in terms of only that.
Doesn't that go through right after linear programs that can be absorbed all
This is
the Ax equal to b, even linear programs can be absorbed. In all of them.
yeah, all of the linear programs. In fact, all of the programs that I've talked about can be transformed into SDP form.
Sorry, no, the constraints can be absorbed just like you mentioned, right?
Yeah.
It can be done for all of them, not just SDP.
Yeah, true. For all of them can be constructed as LMI constraint, and yeah. So one example is max cut, and Alex has spent some substantial time talking about it in class. So I will not be doing that again. Eigenvalue minimization. Minimize the lambda max of a where this matrix AX equals to sum of AI XI, and all the AIs are symmetric matrices. So in order to do this, we need to transform it into this form. Again, this is done by the magic trick of change of variable. This is equivalent to we define there's a scalar t that is always greater than lambda max. In lambda max here, then this is equivalent to say A is smaller than T identity. And that means if we subtract the T times identity matrix with A, then we'll get a positive semi-definite matrix. So this is almost the same as in linear programming when we try to do this kind of thing by making an objective, complicated objective, a constraint. So after we have that, we'll be able to, well, rewrite the programs as minimizing T over X and T subject to AX. And this is exactly an LMI form. Right. Okay, let's do it. I have 1 minute. Do we want to do nuclear norm or not?
Yes.
Okay, we start like 5 minutes late, so. So in the nuclear norm minimization problem, we are interested in solving this thing subject to some some constraint on x. And this is just a sum of singular values of x. It's different from eigenvalue of x transpose x by a square root. So well, we use this identity of nuclear norm. So the nuclear norm is actually the same as the object, the optimal objective value of this SDP program. So how to see that? In general, I don't have time to show this, but when x is when x is a square matrix, and when x is a square matrix, we are able to show this in just one line. So this being a semi-definite program, this being positive definite implies that the determinant of this matrix needs to be greater than 0. And this determinant equals to, just like when these are numbers, this determinant equals to the determinant of W1, W2 minus XX transpose. So this thing is positive, semi-definite is essentially the same as this thing being positive semi-definite. And this thing being positive semi-definite can be rewritten as this form. So in this way, then we take trace on both sides. This is yet another definition of nuclear norm. So we're like by doing a change of variable and we can argue that by doing a change of variable, we can argue that this is actually an upper bound of the nuclear norm. So we are minimizing these over W1 and W2, and the left-hand side is equivalent to, there's a tiny gap here. I don't know. I guess we can somehow change this into the objective value here, but I couldn't do it here. Anyway, that's the idea, and many of those papers that deal with nuclear norms start from here, and then they find more efficient algorithm. The last remark is SDP is very powerful in formulating the interesting convex optimization problems, but it's highly non-trivial to transform other problems into SDP if you do not know the right way to do it. Whenever you find a way to solve a non-convex optimization with SDP, it means like maybe a high impact paper. Also, a thing to pay attention to is SDP do not always have strong duality. So as Suber has constructed in class, there are examples where SDP do not have strong duality. So sometimes it's worthwhile to check the Slater's condition explicitly before you apply the strong duality result. So that's all I'm gonna say today. I think we will have to defer the duality theory and the Finchel conjugate and how to derive the dual optimization to next week. Yeah.
What is the complexity of solving these problems?
For LP, you can solve problems with size like 10 to the power of 7 in a routine basis. So it's no big deal. For SDP, if you use CVX, for my experience, it depends. If you are minimizing one norm, you can do matrix like 2000 times 2000. But if you do nuclear norm instead, then you might be able to only solve like 100 times 100 matrices before you run into out of memory. Yeah.
And SDP is I think O and is just Alex mentioned. Is there like a point of fracture? Is that the line that you've drawn? Is it the line of computation complexity?
This line?
Between SOCP and SDP?
Yeah, this line is like the division of art and technology. On this end, all these are like existing technology. And for SDP, it's still kind of an area active area for research. Although this is also turning technology. And SOCP, you can also find it in Excel. That's all I can say. Okay. Thanks.